I'll let him in, then we'll get started.
Heyo.
Hello, everybody. So today's the day I'm always excited about in this class. We'll kind of lead into the reasons why here when we start the lecture part. But yeah, it's going to be a big example today, and an actual example. The last few ones were just quick passes, opening up the software and looking at the basic syntax. So it's going to seem like quite an escalation from that. But before we get started, does anybody have any questions? Okay, I assume the silence means no questions. So today, and the reason I'm always excited when this day rolls around in this class, tying it all together is the main label for today's on the lecture notes for today. So hopefully that's it. Strikes you as something, the goal we've been working towards with all these little pieces along the way. So now that we've seen loops, we looked at that last week. There's some vocabulary terms and how we use the loops, sort of a usage thing, and then the speaking thing that coincides with what we're doing. The textbook goes over those, just a few words, some things like sentinel values are a common one. That's where we're getting input and we keep running our loop until the user gives us nonsense, such as if we're collecting a bunch of ages, we'll say enter the next age and enter -1 when you're done, because nobody is ever going to have an age of -1, which makes that complete nonsense as far as the data is concerned. But it gives us a very clear indicator of when the user is done entering data. So those are called sentinel values. And there's a couple other terminology things like that in the book, but the basic usage is on loops we talked about. So now that we've seen that, we've seen all of the types of tools we need to solve any problem. Wrote up this list a couple times. Work constructs goes beyond IT problems. Anytime we have a problem, can't remember if I use this example or not, but maybe you're sitting around with a bunch of your friends watching some movies or watching a TV show or something. And when a commercial break comes on, it's your turn to get up and run to the kitchen and grab everybody a drink, which is a problem that needs solved. And there are types of things that you're going to do in order to solve that problem. First off, with some sort of sequence to go through, an order that the steps get carried out in. The steps for solving that particular problem, which in this example, I hope I didn't use this one earlier. I tried to switch them up occasionally, but I'm running to the kitchen to grab drinks during a commercial break. You're gonna get up off the couch, walk in the other room, pull glasses out of the counter or out of the cabinet, put some ice in it, and start pouring drinks. And the order really matters, right? Because it wouldn't make any sense to grab the soda, like grab a bottle of soda and start pouring that and then get glasses out of the cabinet, because then all you would be doing, then you just have a mess of soda already poured everywhere. So order matters when we're solving problems. The second one is we need a way to make choices, to select between various options. And the run into the kitchen and grabbing everybody a drink example, somebody might want a glass of water, somebody might want regular Coca-Cola, somebody might want Mountain Dew. There's a lot of different choices as far as what gets poured in each glass when you get to that part of the sequence. Maybe some people want ice and some people don't want ice. We need a way to reiterate a set of steps. Right? In that example I'm talking through here, you're grabbing drinks for a room full of people. Maybe it's like a NBA playoff watching thing, right? So you only have a couple minutes before during the commercial break while the team goes over the next play to get everybody drinks and get back there so you don't miss any of the game. I think that's around this time. I started seeing commercials that refer to NBA playoffs, so I'm pretty sure we're coming up on that season. But the steps for pouring soda into a glass are the same. So you would repeat those steps for each drink that you're grabbing. And 4 is one that it's hard to put a word on in English, but we usually go with invoke or invocation. And that's a way to step out of our sequence, do something else, and then come back to it. So in that pouring drinks example, maybe when you're in there getting the drinks ready, putting ice cubes in the glasses is going to make a lot of noise. Maybe somebody in there hears that and they yell from the other room like, "Oh yeah, I don't want any ice in my soda. It's in the fridge, it's already cold, no need to water it down." So you have to step out of your sequence, make the adjustments, like dump the ice out of one of the glasses, and then go right back to where you were in the sequence. Or somebody changes their mind, like, "Oh wait, it's already past 9 o'clock. I don't need Mountain Dew. Just give me root beer or something with no caffeine in it." So again, step out of the sequence that you're in, make any necessary adjustments, then come right back to the sequence. So not just an IT thing, but IT is about problem solving. So this stuff applies directly to us. And more than that, we have to feed instructions into machines to solve problems, and machines can't infer anything. They can't take anything for granted. Machines are not intelligent, so we often need to focus in detail on those. And we've seen all our parts for programming languages, how we're applying our algorithms here. The languages themselves come with an order. Selection structures and loops we saw last week. Invocation, the pre-built functions that we can call over and over again. We've been using them since day one, but we kind of looked at making our own versions a little last week. So we also have that big picture we've been filling in this semester, right? That overall thing that coming into this class, you have known at least the computers take in input and give out output. And in between is this big bubble where stuff happens. And we're starting to fill in this bubble is what this class is about. So we can erase that arbitrary stuff happens, or I've seen other people that use similar analogies there. They write the word magic in that bubble. And it's something we don't know. We don't have the explanation for yet. So we can just call it we might as well just call it magic. But we're starting to fill that in. We have sequences to go through, a certain pattern. I'll draw it with arrows. And when we get to our volatile storage, memory, so variables and calculations and processing, and the things we're doing in RAM. And then after we do something, get the user's input, do something with it, maybe store it, maybe do some calculations with it. Then we can come through and run a check on it. The selection structures. So maybe one side of that, if the answer yes, the true side on that selection structure, maybe it's like, okay, that's good enough. We can send that right over to our output. Or if the answer is no, we could come down and maybe go through a loop where eventually the loop's going to come out and rejoin that other exit thing. But it might come down and need to call some other process. In the flowchart program we're using, Raptor, we've been using this for call. I think I stated it earlier, the official UML symbol is a box with double lines on the sides. But if you're in a situation where that might get blurry, like printing it out and making multiple copies, or on kind of a lousy screen, it's really easy to confuse that with our regular volatile memory storage symbol. So we are allowed a little bit of wiggle room in our pictures and customization, and something with like a big arrow makes that very clear what is going on with that. But the official symbol is just a box with double lines on the edges. Maybe we'll invoke some pre-made code and keep coming around, have a loop part, and then invoke thing comes over somewhere else, runs through a different flow chart. I'll just draw a couple symbols there. Don't have much room left, and when it gets to the end, comes right back to where it was. And that's all the pieces. Now it's just a matter of putting those together in different orders, in different sequences to solve different scenarios. So we've got the pieces to fully make something that starts to seem like a real piece of software. And that's why I always get excited about when this day of this class rolls around. It's not just something where we hit our run button, and it goes to this top of the flow chart, runs through, and hits the end of the program. That's not how our software as we think of it works, right? Usually we start it. Well, let's take our Zoom call here, for example. Everybody just logged on to Zoom, and we're going to stay here on Zoom doing all sorts of different things until the end of class today, and then everybody hits that leave button to end it and closes the software. So it's not software isn't something that just opens up, runs once, and ends. Obviously, we do have some types of software that do that, but in general, we think of more of an ongoing thing where we start the program, then we keep doing stuff over and over again, different things. We don't just do the same thing every time. And then eventually the user says they're finished working, and then we're done. Then the software closes. So it like keeps going until the user's done. So today is a big example of a full piece of software is what I had in mind. There's one more piece we will need. I think this is actually listed as module 7, but I wanted to jump ahead because most of y'all need this in your final projects anyway. So this is recapping where we're at, which is basically we've seen all our main points, all the types of tools we have, and then there are some refinements. First one is a refinement on output. Right now, all we know is how to send output to back to the user, and that's really not going to cut it in today's example. So we'll jump ahead a little, and then we'll also see another refinement on our RAM, our storing. When we store things in memory, there's an improvement, which, yeah, for preview mode, the fact that I just said that in plural form, when we store things, not just a single item. So that's still to come. Is it okay if I erase this recap stuff? I'll give it a second in case anybody wants to take a picture.
That's exactly what I did. I took a quick screenshot. Thank you.
Yeah, screenshots are great, pictures, and then you have that to reflect back over. I always found it useful to write things down myself, sketch pictures in a notebook and stuff, and just general note taking. Like I never did a thorough example, but I always felt like the doodles down the margins of the page helped me study come test day. I'm not sure why.
Me too. I like to annotate books too. Like if I own a book, I know that's kind of like a sin. Some people I like to write in my books, like if I like something.
Oh no, it's that's what books are for. That's why we have mass produced books, right? And
yeah, exactly.
In 1200 AD, that was kind of a problem because the book was a precious thing. But ever since Gutenberg made that invented the reusability printing, books are disposable. We can write in as many as we want, and if we need a fresh copy, we can just go get a fresh copy. But whatever helps you remember it, we all think a little bit different. That's one of the things about your way through school is finding what works for you, because we all do think a little bit different. So there is one other piece we need for our example today to kind of tie things together. So far, all of our data has just gone to volatile storage. We either maybe put some constants into variables so they're unuseful names when we write our program, or we ask the user for something, we stick that in a variable. Then when the program runs and hits the end, it's gone. Right? If we need it back, we have to run the program again or ask the user for that data again. Input comes straight from the keyboard or mouse, and the output goes right to the screen. It doesn't stick around for the next run of the program. We have to repeat all those steps. So one more piece that was actually on module 7, not persistent data. But a lot of y'all are going to need it for your final projects. So I wanted to go ahead and jump over this. Is persistent data. We want that data to stick around. So real quick here, let's look at the steps of what we do and kind of analyze the situation. Right? Probably keep hearing that word in college. All your college courses, analyze and analysis. And well, college is studying analytical knowledge, which and analysis itself means to break a problem down into pieces, examine each piece individually, and then build understanding from those, understanding the individual pieces. So break it down into pieces, understand each little piece, and then when you put it back together, you understand the whole. That's analytical. That's the analytical approach, which is what we study in college. That's why you keep hearing that over and over again. So as we talk about persistent data, let's look at our steps for when we need to keep data around. So we start a piece of software. I'm just going to use the text editor here. I have the Atom text editor. I've been very happy with that, but also this is an open source one, and I am very, very familiar with the language that this was coded in. So anytime I need something, I can just grab the source code and make sure it fits my needs.
Is
exactly.
it Rust?
But it's a pretty good one. This one was built as a community project on GitHub. So thousands of programmers contributed to what would be nice in a text editor, which is where we write our programs, right? We write most of our programming languages are still text-based things, so we need a text editor. If we need some data, such as a Python script, we open a file and add our data to that file, or write the data in the file. I'll just print hello world. And then I'll pause. Here's a good way to pause a Python program. Input, press enter key to end, to exit. And then, so if you're doing things in Python and you want it to pause at the end before it finally hits the end of the program, this is a good way to do that. So just ask for input, and then the interpreter will sit there and pause waiting for input, and but then nothing happens with the input. So whenever it gets that input, then the program ends. So then once we write our data to the file, we save the file. I'll call it sayhi.py, and the extension just tells the computer it's a Python script. And then we close the file, which is kind of an important step. Far more important for what we're coming into, that a lot of us as humans will take it for granted, right? Let me open this back up just for a quick example. So say over here, have this file, a bunch of stuff in some file, things written in a file, and I need to go add more stuff. But need to add some more stuff to that file and go to type. I need to get over here anyway. Go to type in that file and start doing this, and nothing's typing in the file. I think we've all done that before, right? Your cursor is not where you thought it was. As intelligent creatures, we will notice that immediately and make the adjustments. A computer will not, right? It's not an intelligent creature. So wherever its focus is, if we tell it to write some stuff, it's just going to write that stuff, whatever it's looking at. So if we forgot to close the previous file and then tell the computer to do some other stuff, it's going to keep doing it in that file that we forgot to close. So it's even more, it's really critical that we focus on that step, which we usually take for granted as humans, but it's, hopefully it makes sense that the computer won't notice that it's typing in the wrong spot. So here's that program. So if I run that, so I just double click to open it and we get the stuff printed out, and then that pause, because yeah, without pausing, the interpreter would just hit the end of the program and close down. But maybe we need to edit that. So I can go back in here and open with Atom text editor. And we can make some adjustments to it. So our data is still here, right? Even though we already finished the run of the program and closed it down, our data didn't go anywhere because we went through those steps. We opened the file, wrote some stuff to the text file, hello world, and some more words, some more stuff. Then we saved the file, save. Then we close the file. So the data persists run to run of the program. So that's kind of an important thing that we might want to do in our programs. Most of y'all's final projects kind of involve that. That's why I decided to move this up to, I think we're still in module 5 instead of waiting to module 7 for it. That way you're not waiting for a critical part on your program at that last possible, that you have to shove in at the last possible minute. So we need to do those same steps. Persistent data, we open a file, write to or read from the file, then close the file. So analyzing that situation that we're all quite familiar with, just breaking it down into the simplest steps, which in a classroom is kind of important. And we're looking at examples like this, but remember what we're studying here in the case of software development, because that's the label on this class, but it applies to a lot of the other IT stuff as well. People come to college and study software development because it's a good paying job. And it's not a good paying job for typing, right? Jobs where you just sit and type don't pay as well as programmers. The reason it's a good paying job is because it's a thinking thing. It's an analyzing thing. We can solve problems. The typing is just the tedious busy work at the end. It's more of a thinking about how we do this stuff. So we go over the process here, but we're under very tight time constraints in the classroom. So all of our problems have to be kind of small. Otherwise, that way they fit in the classroom and we can go through a lot of examples and get some practice at it. Remember, after you graduate and you're out there working, you're going to be facing much bigger problems, right? Problems where you're not just going to open up a text editor and immediately type some Python code. Before you do that, you spend 2 or 3 months just staring out into space thinking, how do I do this? What am I supposed to do? And right on the edge of a panic attack, trying to figure out how to solve the problem. And then once you get it figured out, it's just a couple minutes to type it up. So really, this is a thinking thing. And that transfers over to most of IT. It's a good paying job because it's a thinking thing, the figuring it out thing. And we go through examples. So when we go through examples like this, maybe not the details for opening and writing to and closing a file, but that process we went through to figure out what those details are. That's the stuff you want to look into. So we need to do this with our program, which obviously requires some high-level machine stuff, right? We have to take things from the silicon RAM chip over to the spinning magnetic disk drive or solid state drive. And there's a whole lot of hardware stuff going on. So it's built into the machine, which means it's built into all of our programming languages. The programming languages put together by some of the best programmers in the world, they already took care of that part for us. So all we have to do is ask for it. It's a pre-built function in all of our languages, because it gets a little more complicated. We're changing between mediums and all sorts of stuff, right? We haven't fully moved to solid state drive. There's still a lot of spinning things around. So that makes a better example still, until we don't use those at all anymore. It has at least been recent enough that y'all remember the spinning magnetic disk making noise, and versus the switch to the solid state computer where it was nice and quiet. But we have to switch formats. We go from that electric logic gate thing happening in the CPU over to the magnet, the electrical part over to the magnetic disk and read write heads. So we switch formats, and all that stuff has to be pre-built for us. So it is in every one of our languages. We just have to ask for it. I guess the other thing for the notes is we're introducing unified modeling language, our international standard of communication, and long-term storage. Our symbol for that looks something like this. That's the way I always draw that side really quick. Let me do something like this. I've seen it listed both ways. Some people say it's the actual official documentation says it's supposed to look like a stack of the old reel tape. Those great big tape reels from the 50s or 60s. It's supposed to look like a stack of those. But by the time UML was created, the reel tape was a little out of date as well. So a lot of people just go ahead and say that it's supposed to look like a stack of disk drives. Before long, it'll be like our save icon where nobody really knows what either reference means. But a stack of disk, a stack of circular, cylindrical things is our UML symbol. We can see that. That means long-term storage. So a quick pass at the basic syntax on how we'll do that in Raptor. And then we'll get into our example for today. So I'm going to do another trivial example. So I'll use that standard configuration check, print out the words hello world, because if we can print words onto the screen, we know everything's configured correctly. So that's usually our first, that's the standard first step, is just print out some words to the screen or wherever we're going to check all the configurations before we do something more complicated. So this is the situation we have been in, right? We have, well, let me save that somewhere. Our message is hello world. So basically we're just outputting that. So we save that message and then we output it. And this is where we've been at. We stuck it in volatile storage over in the temporary RAM where we're going to work with things. And then when we're done working with it, we output it to the screen. But we might want to keep that around. So the way it's done in Raptor is we can change where the output goes. Right? We're programmers. We tell the machine what to do. We don't have to, just because Raptor defaults to printing to the console doesn't mean that's where we have to print to. So we can change where that output goes. So this is set up to, if I start typing it, you'll see there's options of redirect output and redirect input. So instead of going to the console, whoops, if I could spell it correctly, I'm going to redirect output, and notice it says yes, no, or a file name. If we know explicitly what file name we want, we pass that in as a string. File names and file paths, it's pretty much standard across the board. The only exception I know of is in cascading style sheets, which you all will probably encounter at some point. But it's pretty much standard across the board. Anytime we have a file path or a file name, it goes in as a string. So when we're programming, we need quote marks around it. If we know exactly where it goes, we could say like, go to the test.txt file, which that's what we're going to do in our example here in a moment. I'm just going to put yes here to kind of show something, because we can also put yes or no in place of true or false. And then we're sending our output somewhere else, which basically opens another file. If we put a file name there, it's going to go open another file and then put the focus there. So that, well, kind of like I showed with that typing in the wrong spot, right? Focus was over on the file explorer, and I was trying to type in the text editor, and it didn't do anything in the text editor. It just moved focus. So instead of having the cursor over here in the console, it opens a file and puts the cursor there. So when there's some output, it types stuff there instead of on the console. And then that critical part is we don't want that to keep happening. So we do need to save it along the way. This is just a scratch one to show the syntax. So after we're done, we'll redirect our output and just say no or false. False does work, but yes and no make a nice the languages that allow us to use the yes and no instead of true and false kind of have a nice flow the way we work through them as humans. And the language Perl did that, and Raptor was originally built in Perl. So if we just say redirect output, let me stop this. Go through this slowly. So we set up our data locally. You see it over here in the one, and then we redirect the output. If we had a file name, it would just go ahead and open that. But we didn't have it a file name. We just said yes. So you see, we got that regular browse to a file box. So I'll go in the delete folder, and I'll right click and make a new text file. Where's text file? I'll call it test123. And then select that file, saying that's the one I want to write to. And you'll notice over here, we didn't get any output on the console because, well, y'all know what happened here. Everybody in this class has seen writing files. We just had the computer write the file instead of us. So our words went over to the file here instead of the console. And we can do the same thing with redirecting input. So I'll redirect input, and again, if we know exactly what it is, you can type that file in. I'm just going to say yes so that we get the box to search for it. And the thing with the input, though, is we need to do it as a loop. Because, well, this example only has one file, but, well, here's the one from when I was getting ready. Our example in class is going to have lots of lines in them. We'll see that soon. I think I meant to delete those before we got started today. That way it doesn't get confusing. I'll delete it when we get over there. So we only have one line, but we might have more than one line. So there's a pre-built exit condition on our loop in Raptor called end of input, which most of our languages also have that. When we're reading a file, there's a pre-built condition that says end of input. Or I personally, since that's a little different in every language, what I usually do is just put it in a loop. And the Python loop actually does this. I'll say while true, so it's an infinite loop, and then like read stuff, because eventually there's not going to be anything to read. It's going to keep reading lines, and then eventually it's going to hit an error. So instead of that error being a problem, I just use that error as the signal that we've hit the end of the file. But that is consistently built into all of our programming languages. And that's what's going on here. We can say, call this exit condition end of input. So that when we're done reading from the file, then we can, we know we're done reading it, or we've gotten everything from the file, and we can shut off our redirect input. Which in Raptor, we just say no. So yes, we want to get input from someplace different than a prompt, which is going to be a file. We'll keep looping around until we get to the end of the file. And then when we're done, we'll close the file. Then each time through, if we call an input, well, this prompt box up here, that's where we'd always tell the user what we wanted, right? Give us the next value. And then the user knows what to type in next. But the computer doesn't need that. We told it to read a file, so it's just gonna it doesn't need further instruction on what to do from reading from that file. We do have to put something there. So what we put there is just quotation mark, quotation mark. So a string with nothing in it. We actually refer to that as the empty string. Something has to go in that box, so we put an empty string there because the computer doesn't need the computer doesn't need prompted. We already told it what to do. And then we'll put it somewhere. I'll put it in a variable called stuff in this case, and then just output that. So I'll do that thing for good form. I think we've seen this now, right? Clear the console, so we get rid of all the junk there. And we'll write to this file. Write the data we have to that file. And then since we're just looking at syntax here, we'll immediately read that data back in and print what it is out to the console. Or make that a little bigger. There we go. So it goes through our steps, clears out all that stuff. Where are we going to write it? I'll make a new file. And when you do this in Raptor, it does not have the ability to create a file. So when you're over here in the browser, make sure you do like a right click and create a new file. It cannot automatically create a file. If we just give it a name, it will automatically create it. But yeah, this uses the box that comes from Windows. And when they the programmers at Microsoft put Windows together, they did not give this box the ability to create a file without calling that other stuff. Yeah, I'll just put it in a new text document. That'll work. So put it there. Goes over there and writes that. And now we can select from one of these to read from. So we put it there. Goes through, grabs the stuff from the file, and spits it out to the screen. And the data still works. So I could take this writing part out and just go with the reading part and close the program, come back to it, and that data is still around. So kind of an important thing. Some of y'all are going to need that on your final projects. And it seems like a good way to handle our class example today. But so not much to it. Same steps we normally do. Open a file, which if you want to jump ahead, it's listed in the module 7 homework, but there's a lot of stuff to do, so you might want to wait till we get there. The keyword in Python is just open. Open file name. And you do have to go with the file name in Python, because getting that box from the operating system is a little more complicated in Python. They didn't build that in the background for us. So open file name, you'll do your write stuff, and then your keyword at the end is close. So it's in the module 7 stuff, so coming a little ahead, but I wanted to go ahead and include it because it's kind of one of the last big pieces, right? We need our data to stick around. We don't want to just use the data once and throw it away. What time is it? 1:41. Okay. I was expecting to be here a few minutes ago. Is it okay if I erase the board here? I assume the silence means that's okay. So same steps we go through, and the process of listing those out on the board, that process is the important one overall, right? We're in a thinking field. We need to be able to break that, to repeat that process and figure out the steps for something we've never done before as well. That's just an easy one to analyze those steps on. And the UML diagram, the thing that looks like a stack of cylinders is the symbol for long-term storage, which actually would have been a really nice one in this week's, for some people on this week's UML diagram assignment. Because what you're supposed to draw a picture of involves things that are probably, some of them are probably going to be in long-term storage. So having seen that picture last week would have been nice for that. So you don't necessarily have to include it, but hopefully you realize where that picture would have gone in the UML diagram. So let's see what I put in my notes. When we get to this point in this class, I like to use an example that reaches into another class in your IT studies. So got a few in mind. This time it's come back around, then alternate between. This time we've come back around to a network administrator example. Some of y'all may have had your intro to networking class, netting 105 or 109, depending on which pathway you're on. Wait, it's not 105. 109 or 114, I think. There's two different intro to networking classes. The 109 has follow-up classes, whereas the other one where you only have, if you take the 109 class, you have to take at least 2 networking classes. They spread it out, spend a lot more time focusing on it, whereas the other one, it just shoves it all into one semester. So whichever one you might or might not have had that yet, but I like to do this because it's kind of important. We're all studying a specialty in IT, right? That's why you're here. Some of y'all are studying to be a cybersecurity specialist. Some of y'all are studying to be software developers. Some of y'all are in the IT support, different specialties, but the entire field does go together. And there's lots of overlap between those fields, right? Cybersecurity people are going to have to deal with networking things and program and software things. Networking people have to deal with the hardware, software, server administration. And there's a lot of overlaps. In other words, the classes aren't completely separate subjects, right? They're all classes in the IT subject, and material from one will blend over into the other. And I've seen a lot of people stumble around on this when they get to the higher classes, especially, because once you hit about maybe 230, numbers are around 230, 240 and above, they'll just go ahead and assume that you've had all of your 100 level classes. Maybe 250 is a nice cutoff point from that. From 250 and above, they're going to assume that you've had all of the 100 level classes you're supposed to take. So then they'll just throw in things that you would have seen in your other classes. For example, I was helping somebody a couple weeks ago with a problem, and I think it was an ITSP class, but the particular assignment needed a relational database. And this was one of the classes at the end. This was like one of the 270 ones, one of the systems analysis ones. And she completely confused because the class hadn't said anything about databases up to that point. And then suddenly she had to have one to make the hardware work. And this person was about to graduate. So it's like, well, you've seen this in other classes. We know all the pieces from your SDEV 111 class. You know how to go to AWS and set up a Linux server and just throw a Linux server on that. And from your DBMS 110 class, you know how to create a relational database. So you need to go do those steps, and then you can come back and do the next one from here. So you'll see some of that as you get further along too, where the instructions are just like, well, I think that was an ITSP class. It might have been one of the other programs, but it was very hardware oriented, where the instructions are just like use a relational database, and you kind of have to pull information from your server administrator class and the database management class and go build the database before you can even carry out the step in the homework assignment that you're looking at. So more and more of that gets taken for granted the further along you get. But there's that overlap, right? We have those specialties, but there's specialties in IT. So anything from IT is fair game, might be one way to look at it. And keep that overlap and crossover stuff in mind. So that's why I pick these examples that kind of cross over. So this time around, we're back to a network administrator sort of example. So here's the problem, or a quickly made up version of a problem we can solve. Small company, with 5 or 6 offices in region. IT guy needs list of all machine addresses. I'll put it that way. So if you'd like some details, maybe like a fast food franchise. Somebody owns 5 or 6 McDonald's in the area. So every one of them is going to have a bunch of machines, right? They have all their point of sales things, which traditionally has been called POS, but we always need to, that means something else anymore as well. So we always have to explicitly refer to the point of sale, the cash registers, the computers in the office, the printers, and everything tied into that company network needs tied together. 5 or 6 different restaurants around town, or other types of offices, whatever the business is. Several offices in the region, small enough that 1 or 2 IT guys can handle the whole thing, but they're in one location, right? So if the IT guys are at the office in, well, I'm going to use the region I'm in here close to Sellersburg campus. If the IT guys are in New Albany and there's a problem at the store in Jeffersonville, they might need to remotely access that machine in order to do it. So they need a list of all the machine addresses on their network. A very oversimplified example here. But we need to create that and maybe just generate the IP addresses. They can assign them once they have them, and our software will keep a track of them. So we'll go ahead and have our software generate the list, and then the IT guys can assign it, but we'll just have, and really read the list once it's on there. So sort of stepping back over into network stuff, and basically what we want is software that will create several lists of IP addresses, machine addresses, how we locate a machine, and store them so that we can pull it back up and see all the IP addresses we have in a particular office. So an IP address, if you haven't had your networking class, I'm going to go with IP version 4 address. We need a way to locate every machine. And let's use, for an analogy, the way a delivery guy would find you. So a delivery guy or lady needs to get a package to you. And they'll use a 4-part address that gets more specific as we go down, right? They'll look at what state you're in. Then after they get that through their logistical system to the right state, then they'll look at what city you're in that state. And once it gets narrowed down to just the particular city, it gets handed off to the kind of final delivery guy that then takes it to your street address. And all right, I'll in there. And if applicable, we might need to go one step further to an apartment number. So that's how a delivery driver or postage or anybody can find you. What state, the 4 different things to get more specific as it goes down. And computers use the same system, only for a machine, it's going to be all numbers. That's a very high level way to look at it. But for example, the website Ivy Learn, where we go to see what our homework assignment is and all the course policies and all the things like that. I know everybody in here has been to Ivy Learn. So when we need to go there, go back to Raptor. Sure, save that. That's just going to be deleted. When we need to go to Ivy Learn and check it, we open up the browser and type in the words ivylearn.ivytech.edu. But those words are just there to make it a little bit easier for the human to deal with. Because, well, we saw a couple of weeks ago talking about binary data, even when it's words, the computer treats that as a collection of numbers that are encoded to represent symbols. Each symbol is represented by a particular number. When we get on Ivy Learn, we can do all our course stuff. But the machine doesn't use the words. It uses numerical values, a combination of them. So if I run NS lookup on that. So I'll go over to my bash shell running my computer here. And if anybody's like, sitting through this class because it's on the requirement list and you know what a bash shell is, and like using bash shells, and notice that I'm running a Windows system from a bash shell, see me after class and I will show you how to set that up on your Windows machine.
Are you using like putty or Excel or?
No, I'm using bash.
Just bash.
Yeah, I'm just using bash. It is a full bash. It is a bash shell. It's just running Windows. So has some nice advantages. Use the same language to control every operating system. And use that on the Chromebook, the MacBook, the Linux machine, Windows machine, and use the same language to control all the operating systems.
Yeah, I know bash the best.
Okay, I can show you that.
I don't know a lot, but I know bash the best.
So if you want to stick around at the end of class today, I'll show you how to set that up on a Windows machine. It's really, really easy. It's pre-made for us.
For sure.
The only thing that's missing, it actually comes from GitHub. The only thing that's missing, like it's an official release from GitHub, a release from Microsoft, they own GitHub. So it's official software, but the only thing that's missing is admin access. So I'll show you how to do add admin access to it. And then you have Bash to control your Windows.
Would it work inside a Windows VM?
Yeah.
Do you think? Okay, cool. I don't know if there's any.
Yeah, if you want to practice with that, but yeah, that was just a side thing because I know some people are, well, when I came back to school, that's how I was. I've been using computers for decades. I knew lots and lots and lots of stuff about them. Really, the learning comes from, I know so much about computers because I broke them so many times. Give it a try.
Same.
See if it works. If it doesn't work, fix it. And that's when you really learn about machines. I've done that so many times that I didn't have any paperwork though. So that's where I was when on my way through school was like, okay, I know lots about machines, but I got to have that paperwork to get a job. So I know some people are in here like that. So that was kind of a comment for them. So I just ran this instruction. So back to where we were, and yeah, stick around after class. I'll fill you in on that if you want, if you're curious about using that. So that's the human form. Nice words. They all have meaning to us, make a lot of sense, but it doesn't make any sense to a computer. A computer needs some numbers to pass through. So the computer uses this set of 4 numbers right here. Well, there's 3 of them. That's a big one. So there's some fallbacks. It automatically tried to connect to 3, and on something like Canvas, there's 3,000, so 3 or 4,000. That way, at any given time, millions of people are able to connect. But kind of like that street address that I mentioned for how a delivery driver would find you, there's 4 parts, and each one gets more and more specific until you can narrow down to the exact machine you're on. So for example, Ivy Learn, US East 1 at AWS. So this is over in Central Virginia, Northern Virginia, the middle of Virginia. Virginia looks like a bell curve, right? There's that big hump in the middle. So there's a great big server farm, a warehouse just filled with servers there. And that website is actually sitting on there, and the computer finds it by this 4-part address. So that's what our example software is going to do, is going to create a couple of those. Create a list of those for like 5 or 6 local offices. Something small enough 1 or 2 IT guys could handle it. Seemed like a good little crossover example. We see a little bit of networking stuff and finally see a full example of programming, right? Our last few examples were like that one we did earlier when we opened up Raptor. We just did the most basic stuff possible in order to see the syntax for the language. So now we want to do a full example. And a business with say 5 offices is probably going to have 3 to 8 employees at each office. So what's the middle there? Like 5. So 25 employees. So they'll need 25 computers, 3 or 4 printers, routers, and other equipment plugged into the network. So we need a big list of those so the IT guys can keep all of the machines straight. So that's the software we're going to do for our example. And finally, a full example. That's why I'm always excited about this, because it's not just going to be, we have this program that we hit start and it runs. And then we hit start and it runs again. Then we hit start and it runs again. We're going to hit start and it's going to keep going. And then eventually the user is going to say, I'm done, and exit the program at the end. So like a full piece of software example, which takes us up to 2 o'clock and probably a good break point, because the next thing in my notes is the planning phase, because we haven't gone through that in a moment. Once again, the big thing here is the process of thinking, right? Our examples have to be small or they wouldn't fit in a classroom. But the reason these are good paying jobs is because when we understand that process, we can solve problems that have never been solved before and aren't specifically designed to fit in the time constraints of the classroom. Really hard things where we might have to spend a couple months just staring off into space thinking, how do I do this? Where should I start at? And yeah, just spend a long time thinking about the problem before even even beginning to address it. In the real world, we have big problems like that, but obviously that can't fit into the time constraints we're under in a classroom. So we have nice small problems in a classroom. But this seems like a good break point. So why don't we take a 10-minute break, and then we'll go through this example afterwards. Does that sound good? 10 minutes sound good to everybody? Or anybody?
Sounds good to me.
Okay, so it's
Gonna make some
2:01.
coffee.
We'll get back to it at 2:11. Yeah, I've been talking for an hour straight, so I could really use some coffee. I will see y'all in just a few minutes.